Okay. Hello.
Hello.
Okay, and let's get back. So last time we talked about this matrix representation of any linear operation. Any linear transformation. So operation is from a sense space. Transformation is between two, maybe different spaces. So we have any linear transformation between Rn and Rn, and we say that you can always represent it as a matrix A. And to transform from Rn to Rm, you just take this Rn vector x and multiply by your matrix A. And we give a very very constructive proof of this theorem. We told you how to find this A, so this is something you need to remember, and will be in your homework and final. So how do you find this A is you can calculate the columns of A one by one. So you just take all the standard basis vector inside Rn, so those Ej is a loss vector with only j's element being 1 or other element being 0. So you take those Ej and you put them into this linear transformation that must be given you somewhere. Okay, so you put Ej into linear transformation, then you will get mapped to something inside Rn. And so this m-dimensional vector Aj, so this j is same as this j in Ej. This will be the jth column of your A. Okay. So you just do this one by one, and then you can calculate each column of A and put them together. You will get this n by n matrix of A. Okay. So so we see proof, and we see some example. So we have this linear transformation, and we see that we put the E1, E2, E3 inside. Then we get this A, and we have that AX is exactly what we expected as the outcome. This is x1 plus x2 and x2 plus x3. Okay. And we also see that we can do, with this definition, we can calculate the matrix that will do a rotation in R2. So this is actually a linear operation. Okay. And last time we end on this question of, so the theorem we just talked about was from Rn to Rn. And so those are Euclidean spaces. And but we also say there might be abstract vector spaces. So if we have a linear transformation between abstract vector spaces, then can we also write the transformation as a matrix? And the answer is yes, and we do it in a kind of lazy way. So basically, we map any n-dimensional space and any m-dimensional space to Rn and Rm by finding order basis for each of them. So we have order basis E, and with each element called V, and that's that's the order basis for this vector space V, and also order basis for W. So the set is called F, and each element is called this small w. Okay, so we have an order basis for V and order basis in W. Then basically we can write any vector in V and any vector in W as a vector in Rn and a vector in Rm. That's because you always know that we have this when we have an order basis. So back in chapter 3, we said that when we have a border basis, we can calculate something called the coordinate. So any vector inside V, so a small review on chapter 3, any vector V can be expressed as a unique linear combination of your order basis. So you have V equal to this, every V is equal to some x1, x2 to xn, and x1 times v1 plus x2 times v2 over to xn plus vn. So this x exists, and they are also unique. Those are called the coordinate. Okay, so this is a coordinate of this small v in terms of this E basis. Okay. And similarly, you have any vector inside W can have a unique coordinate, which is a vector in Rm. Okay. And so now we have those two coordinates. Then those two coordinate mapping. Then the theorem is pretty obvious. So we also have the linear transformation can be represented by matrix A. So I should highlight it here. So once again, we have this matrix A representing our linear transformation. Okay, let me take this out. Oh, also, sorry, let me try to fix this thing. Okay, nice. Yeah, so we have this matrix A here that correspond to our linear transformation, and where is? Oh, I forgot to do this. Excuse me. Try to connect this here. And, yeah, so matrix A represent our linear transformation L, and now this representation depends on what order basis you pick. So you have pick and B, E and F here. Okay, and anyway, so we will have AX equal to Y if only if X equal to Y, and Y will be the coordinate of your L order V. So yeah, so you have V, which has a coordinate X, and and Y will be okay, and Y is the output, is a coordinate of L order V. Okay. So yeah, so you have V and L order V and X and Y. V and L order V, and they each have a coordinate X and coordinate Y, and X and those coordinate X and Y will satisfy this AX equal to Y. So you can calculate the transformation between coordinate by just multiplying this matrix A, and then we know every vector inside every vector inside big V and every vector inside big W can be represented, have a one-to-one correspondence to those coordinates. Okay. And yeah, and yeah, as we said, so Y is yeah, Y is given by L over V is the coordinate of L over V in terms of this basis F. Okay, so Y equal to L V equal, and yeah, let's see this in picture. So I guess there are a bit of too much drawing. So yeah, so this so let's not read not look at the handwritten thing first. Okay, so yeah, let's read those non-handwritten part first. So we have V to W. So this is what we originally have. Excuse me. So we have abstract space V and big V and abstract space big W, and some vector inside V will get mapped to some vector W equal to L over V. And we say we can map V and W to R and Rm by looking at those order bases. So we have order basis big E and order basis big W. Sorry, order basis big F. And so each VC inside will have coordinate X, and then this W will also have coordinate W of F. And yeah, so this is also called Y. Okay. I guess here we should write W of F equal to Y. Okay. Okay, so this equal to Y. Let's see, it's a bit cramped here, so maybe right here. So we also have this Y vector equal to this W vector, and in F coordinate. And we say that we can represent this transformation by just writing how this X and Y correspond to each other, because we know this X and V are one-to-one correspondence, and this Y and W are one-to-one correspondence. And how is X mapped to Y is that there is another matrix A. So now this A is a matrix of L. Okay. So I think this here I should really write the other way. So it's more like A sub L instead of L sub A. Okay. So L is just something given, and you have A, that's a matrix that depends on L. Okay, and yeah. Okay, so that is what happened. And just like in the previous section, now we want to think about how to find this A sub L. Okay, and yeah, so now the question is what's A sub L? And I guess then the handwritten part kind of already give the answer. So basically we want to do the same thing. So in the previous section, we said that if we just map from Rn to Rm, then we can find A sub L. Then we can find this A sub L by finding the column of A one by one. We have that A sub L. The first column is L of E1, and the second column is L of E2, etc. Okay. And yeah, so we also have L here, and we have Rn to Rm here. So basically, we want to see how the mapping goes inside this Rn to Rm to find each column of A. Okay. So we want to see what. So we want to look at all the computational basis. All the standard basis elements here. So those EJ, how do they map to AJ? So EJ in Rn, how they map to AJ in Rn. Okay. So now we need to get I guess a detour inside this square, because we have a 1-to-1 here and a 1-to-1 here. So we want to go to EJ to some AJ, and but we only have this mapping defined. We don't know this A yet. So how we find the A is we go EJ, and we know EJ will correspond to some VJ. Okay. So yeah, because EJ is well, you only have a J's coordinate. Then you map to this order basis. You see that you pick about the J's element of this order basis. Remember, we have the order basis here. Okay. So we will have so this order basis here. You think about if you have a coordinate being just EJ, then the corresponding vector inside V is just VJ. Okay. So what we do is we start with EJ here, and we want to see what the map AJ is. So we go EJ, then go to VJ. And VJ now in this abstract basis, in this abstract space, we know how V vector in V map to vector of W. So VJ get mapped to L of VJ, and then we transform back to Rm. Okay. And so L of VJ will get mapped to this L of VJ of F. Okay. And yeah, this is something we know how to do in chapter 3, and we will review this a little bit later. But for now, we know that L of VJ also corresponds to some unique coordinate inside Rm by this F order basis, and we write it as this. So that's L of VJ of F. And I guess we need to say a little bit of notation that I forgot to say. So we have this kind of notation to write coordinate of a vector with respect to some basis. Okay, so I think we talked this a little bit in chapter 3, but didn't stress too much. But yeah, remember this kind of notation means coordinate with respect to order basis. So this is coordinate of this vector V with respect to E. So this is basically how map this V to this X here. And also similarly, this is the coordinates of W with respect to F. Okay, so this is basically mapping from W to R. Okay, so we have those two things. And with this notation, we see that AJ is L of VJ with respect to F. Okay, and yeah. And yeah, that's exactly what we'll do. So now how we find the representation of A. And yeah, so let's see this all written down in in a lot of algebra, in a lot of symbols. Okay, and yeah, so we want to find, as we say, we want to find AJ. That's coordinate vector of L of VJ with respect to W. Okay, I guess here we define this thing. So yeah. and I guess we want to verify the result is correct. Okay, so we already have AJ equal to L of VJ with respect to W. Okay, so this thing, coordinate vector of L of VJ with respect to F. Okay, and yeah. And so we will have L of Vj will equal to this linear combination of basis vectors of W of F. Okay. And yeah, then we write our A. So A, as we say, is listing all those AJ as columns. So A is A1, A2 to AN. And yeah, and we'll calculate L of V and see that it actually works out as our A thing. Okay, and now we go the other way around. Okay, so now we already defined this A of L, and we want to see our L of V actually works with this A of L. So I think what we want to do is now we go other way. So we have some V here, then we'll map to X and do this ALX and map back and see that actually equal to L of V. Let's see. Okay, let's see what do we have. Okay, so L of V equal to L of all those linear combination of V. Okay, and it's well, it's a linear operation and we have a linear combination, so we can linear combination and the linear operation commute, so it's a summation x and L of all the basis element, and we know what the L of all those basis element is by definition this thing. So here we use and use the L of Vj equal to all those some Aijw. Excuse me, Aijwj. I think here we have a typo here. Oh no, Aijwi. Yeah, sorry, I got it wrong. Okay, so I have Aij, so J here, and Wi. So it's on I from 1 to n here. Okay, and then we change the order of summation here. We see that this is some I, some J, and some Aijxj and Wj here. And this is weird. I guess here we do the derivation once again. So we see, so here we do, okay, sorry, gonna be confused. So here we are trying to calculate L of V and trying to see that they actually do what we want. Okay, and anyway. Not sure this calculation. Anyway, so L of V equal to this thing, and and yeah. So now we have that L of V equal to this sum I sum j, and or sum over this some coordinate. So now we can group together this summation and just call this. When you sum over j, this is just some number. Okay, so Aij and Xj are all scalar. So you do the summation, then it's just a number that this is just a number that is indexed by this I here. So we can call this Yi. So this sum Aij Xi. Xj is just a number depending on Y, and we can call it Yi, and we see that this is just the coordinate of L of V. Okay, and yeah, so Yi will be this form, and we see that it works out. So Yi equal to this sum Aij Xj, and we see that that's exactly the ith element of this A matrix multiplying on your X vector here. So if you do this matrix multiplication of A equal to the A we define, and X equal to this thing, then we see that the Y vector will exactly equal to then the the resulting y vector will exactly have its element equal to this thing here. Okay, and yeah, so y equal to x actually works out for your L of v. Okay. And yeah, I guess that's kind of the proof that this works. So we have we define LV equal to this thing. We know LV equal to this thing, and then we can define this AJ. And we see that you put those elements of AJ equal to, or this AJ equal to into a matrix, then L of V will have its coordinate. L of V will have its coordinate equal to this A times X. Okay. I guess this is a quite complicated proof, but it's easier to remember this picture. So basically, we want to go to EJ to some AJ, then we go back to VJ, and we make to L of V, and L of V we make back to its coordinate. Then we need to take this coordinate. Okay. And any questions so far? So written out the theorem then is like this. So we have order basis for V and the order basis vector. Order basis for W. Then we can have a matrix that will transform coordinate of a vector to transformation to the coordinate of the image of the vector V. Okay. And yeah, so this coordinate in F is equal to A times the coordinate in E. Okay, for every V. Okay. And this A is calculated by just looking at how each basis element is mapped into F. Okay. So you have L over all the V, and we need to take coordinate in with respect to F. Okay. And yeah, so once again we have this picture. And if we have no question, then I guess let's try to see this thing works out. This complicated construction work out in an example. And here we have mapping that's defined by this. So we have some R3 to R2 mapping. So I guess this is not really abstract. We have another Rn to Rn, but now we have we can pick different bases for our Rn and Rn. R and Rn. Okay, and yeah, so we have a weird definition of the linear mapping here. So we have L of x equal to x1 b1 plus x2 plus x3 b2. Okay. So basically we have a weird basis in R2 with respect to this b1 and b2. Okay. And b1 is this 1, 1 vector, and b2 is this minus 1, 1 vector. And in R3 we still use the standard basis. So we have x1, x2, x3 corresponding to 3 coordinates of R3. Okay. And yeah, so now we want to find the matrix A representing L, okay, with this E1, E2, E3 in R3 and B1, B2 in R2. Okay, and here this is basically immediate. So we want to see how E1, E2, E3 is mapped by this L. Okay, and yeah, let's not write this, not read those handwritten things. Okay, and yeah, let's see how the square work out. And here we don't need to transform between V and X because V already equal X because we have the standard basis here. And then we map all those EJ to V. Okay. And they will map to 1 times B1 plus times 0 plus B2. Okay. So E1 will get to this X1 times B1, and E2 get mapped to this 1 times b2, and x3 get mapped to this 1 times b2. Okay, so this is 1b1 and 1b2 and 1b2. And we see that because we are given this L in a very nice form, so we already find the coordinate with respect to b1 and b2, so we don't need to do this transformation here. Okay. This is a nicely set up example. So this is a coordinate with respect to f is already 1, 0, and 0, 1, and 0, 1. Okay, so A is 1, 0, 0, 1, 0, 1. Okay, so this is an easy example. Okay. And I guess here we have a more complicated thing calculate. That is, if you want to calculate with respect to E2, E1, and E2, then you can multiply by everything. L of x equal to this thing, and A sub E is equal to this different matrix here. Okay, any question? Okay, yeah, and so this is what we want to do. Okay, and we have another example. Okay, so if we have another R2 to R2 example, and here we also have a nice expression for RL. So we have an expression of a mapping from this B1, B2 basis to another linear combination of B1, B2, both in R2. And B1, B2 is this order basis in R2. Okay? And actually, what the B1, B2 is not important. It's just whatever order basis. And because we already write the coordinate in terms of B1, B2 in the beginning and the end of our mapping, so yeah, so we already find how the coordinate map each other. Okay, so we can have what the B1 map to this. So B1 map, B1 will be alpha equal to 1, beta equal to 0, and you will map to just B1 here. Okay, and the coordinate here, so the coordinate of the image is 1, 0. And if B2, then it's 0, alpha equal to 0, and beta equal to 1. And that will map to beta equal 1. So 1B1 plus 2B2. Okay, so the coordinate is 1, 2. And as we say, we list this as the first column, so 1, 0 here, and this as the second column, 1, 2 here. And we find A immediately. Okay, so those are the easy examples. And now let's see more non-trivial example. Okay, so now let's see some non-trivial example where we mapped from Rn to Rn, and we have a non-trivial basis in Rn and a non-trivial basis in Rn. Okay, and yeah, that's our next theorem, and let's see how we do this. Okay. And so we have another E for Rn and another F, an order basis E for Rn and an order basis F for Rn. Okay. And we want to find the linear transformation with respect to of the coordinate with respect to this basis. Okay. Okay. So this is something like a changeable basis in Rn and Rn. Okay. So we already know how to write the linear transformation from Rn to Rn. Okay. Let's compare a little bit. So jump back. Okay, it's here. So yeah, we have the theorem 4.2.1 already say we have a linear transformation from Rn to Rn. We can write the matrix representing this transformation. We say each column of A is just how map you just map each standard basis element. Okay, and so this is 4.2.1, and now to 4.2.3. We basically generalize this theorem and saying that we have a mapping from Rn to Rn, but we want to write this mapping in different bases. So this is basically a changeable basis. We want to find how this mapping acts on the coordinate with respect to E and F for whatever E and whatever F. Okay? Because we can, and also because sometimes we want to look at things in different bases. Okay? And how we do this then is now we go back to our square, and so we want to find the coordinate of the mapping of each basis element here. So we have all the uj here, we want to map it by L, and then we want to find its coordinate with respect to f inside this Rn. And how we do this is basically we want to multiply this B minus 1 matrix, that's where B matrix is just these all the order bases together. Okay, because you want to find the because we want to find the coordinate of this thing. And why is this B minus 1 is now we need to remember how we do this in chapter 3.5. We say that we have vector x and equal to some basis u times some coordinate c. Then x will equal to uc, and so the coordinate c with respect to this u is actually u minus 1 times on x. Okay, and so this is the coordinate transformation we do in 3.5. And now we have more coordinate transformation. Now we can think of this as the changeable basis. Okay. So now the changeable basis just do b minus 1. And so to do this, we need to be able to remember how to calculate the inverse matrix of this non-singular matrix that's a lethal basis here. Okay, and we basically already done the proof, but let's try to run the proof once again, really quickly. Okay. So basically we do what we do before, and we say L of uj will equal to some coordinate times bj. Okay. And we want this thing to be equal to, okay, and this will be your B matrix times your A vector. UJ. AJ is the vector we want to find. AJ is the coordinate of L of uj. Okay, so we want to find all those AJ, which is equal to coordinate of L of uj, and we calculate what's L of uj in cylinder basis. Let's see, L of uj equal to okay, so L of uj should equal to this thing, and it's writing down a lot of things in weird order. Okay, but anyway, L of uj equal to this linear combination of bj, and we rearrange this matrix, and we see that it is this B matrix multiplied on this vector aj. Okay, and this is all in the cylinder basis of our Rm. And then because of this, we can just apply b minus 1 on both sides, and we see that the aj equal to b minus 1 on L of uj. Okay. There is nothing too much in this proof. Basically, we just do a changeable coordinate, and this chapter 3.5 thing again. Okay, so this is all this b minus 1 doing. Okay, basically this thing. Okay, and if we're okay with the proof, I guess now we can try to do some dirty calculation. Okay. And so now we have some R2 to R3. So now we have full-blown changeable basis calculation here. So we have linear mapping from R2 to R3, and this is defined by this thing. So R2 has x1, x2 vector, and they map to this x2 and x1 plus x2 and x1 minus x2. Okay. And now we have two non-trivial bases on R2 and R3, and we want to see how this transformation do with respect to coordinate of those two bases. And the basis is quite random here. So 1, 2, and 3, 1. And we have 1, 0, 0, 1, 1, 0, and 1, 1, 1 here. And yeah, so this is up to here is the question part. And now we have the solution part. Okay, so solution part, as I say, we want to find L of U1, L of U2 with respect to this basis. Okay, and we want to find, we can calculate L of U1, L of U2 pretty fast. Okay, so L of U1, U2 is already given here, so just calculate L of U1, L of U2 with this formula here. So this is x2 is 2, and x1 plus x2 is 3 here, and x1 minus x2 is minus 1 here. And similarly, you can calculate L of U2, quite straightforward. Okay. And we have L of U1, L of U2, and we want to find b minus 1 on L of U1, L of U2. Okay. And we can do this a bit faster by doing Gaussian elimination with our B and LU1, LU2 together. Okay, and remember we say that when we calculate the B minus 1, we can do this write B and identity and do row operation to turn equal to identity and B minus 1. Okay. And then pretty easy, you can see that if you have B and another matrix A here, and you do row operation to turn this equal to identity, then the other side will be B minus 1 on A and A. Okay, so let's write this. Okay, so don't have let's write it maybe here. So we have B and A. And if we do row operation and turn this side to identity, and then this side will be B minus 1A. Okay. So this saves us some matrix multiplication of calculated B minus 1 and multiplying it on our matrix, this LU1, LU2 here. Okay. And yeah, so but I guess the calculation is yeah, maybe a bit easier. Okay. And yeah, let's do this together. So we have a B here and LU1 here, LU2 here. Okay, so we already have LU1, LU2. And then we just need to do row operation to turn this equal to identity. And we see this is already in REF form, so it's pretty easy to turn this equal to RREF. So you make those two 0, then make this 0. Okay, you subtract up here, and in the end, so we give all the middle calculation. This is the last part of Gaussian elimination, and you should get this matrix here. Okay. Let's see, we subtract 1 here, subtract 1 here, so it's 2 here, and minus 1 here, then we subtract 1 up, and yeah, should be this thing. Okay. And yeah, so we have our A here. Okay. And let's try to see this actually work out. Okay. And we can verify that this A actually works. So we want L of U1 equal to this A, the first column of A matrix, and as a coefficient of B1, B2, B3. And L of U2 should be the should have coordinate with respect to B being this minus 3, 2, 2. Okay, so this minus 3 on B1 and 2 on B2 and 2 on B3. And I guess here we have done some calculation. Okay, so this is B1, B2, B3. So we have minus 3 on B1 equal to this thing, and 2 on B2 equal to this thing, and 2 on B3 equal to this thing, and we add together, it should become LB2 equal to this. So minus 3 plus 2 plus 2 equal to 1, 2 plus 2 equal to 4, and 2 equal to 2, etc. And yeah, you can also check this L of U1 works out. Okay. And yeah, so that's the end of 4.2. So we have see a lot of representation of those linear transformation. So we start with the easy one. So Rn to Rn, we have we say we map each basis element and see what they are, and each basis element will be the image of each basis element will be the column vectors of your A here. And then we see that in most general vector space, arbitrary vectors V and W, then we can write down, represent this mapping by finding a basis in V and a basis in W, and just write down the basis with respect to the coordinates. Okay, so in this square. And yeah, so we have this the coordinate of the image equal to A times the coordinate of the starting point. Okay, and yeah, then we also need to find this AJ, and the AJ we need to find this in very very complicated way. So we need to start from EJ inside this Rn, and maybe to Vj, and Vj get mapped by L of Vj, get mapped to L of Vj, and then we need to find the coordinate of L of Vj. And this is all very abstract, and we see how this work out in now more restricted case, but more generally than is Rn to Rn. We have that we can find the order basis in Rn and the order basis in Rn, and we find out that to calculate this AJ, you need to find the L of Uj just before, and to do this transformation to coordinate in F, you apply this B minus 1 here. Okay, any questions so far? If not, yeah, this is end of 4.2. I guess let's stop earlier now for 10 minutes, and let's try to finish 4.3 in next class. And if we finish early, we'll stop class early today. Okay. Yeah, so yeah, look at this summary of 4.2. It's quite complicated, but I think the idea is focus on this square here. Okay. Yep. Let's take a 10-minute break.他好像下一节课会来，你问他一下。OK， 好，谢谢。 这个是算不同 basis 的呀。这下面的是算说这两个 basis 之间的 transformation 嘛。这个 A1是说如果这个以 B1 B2 换成E1 E2 的话，那它应该是什么样子？对。
哦。
所以只是算了一下。
所以下面是用
B1
B2 当 base，
对。
这里是用
这个 standard， 对。
那所以他们两个应该会插一个 B1 B2 的 matrix， 倍数。
但 B1 B2 应该要插在后面。
B1 B2 要插在后面。
等一下我想想看，不对，插在前面。没有，你说应该是对的。我想犯了，对的。
B1 B2 插在前面。
对，但是谁乘谁我有点忘记，应该没错吧？
为什么后面的公式这里是 inverse 的？
就是算出来是这样，就是可能还是从那个我还没有上传，但是的确之前讲的是这样的，就是3.5从我也记得3.5的话，你要从 standard basis 变成某个 u basis 的 coordinate 的时候，你要做的事情是乘以 u minus 1。
我想想。
这个到底是要负一还是不要负一？是需要回想一下，需要记一下。 啊？什么？
就刚刚有什么特别的市场？
哦，有一个学生说成绩还没有登记的，可能你在干嘛？
是后6吗？
没有，应该是考试的成绩吧？对吧？你等一下下课，因为我们刚刚提到下课，所以我现在准备开始讲。对，所以，对，然后还是你们先讲完，好，这样过来，你们先讲一下，然后准备开始，就是这位。Okay. Let's get back. Yeah. So those are all the representation of linear transformations we have in our 3 theorems. So 4.1 and yeah. So basically you map the basis elements to basis element in your V to something inside W and try to find the coordinates. Okay. And that's 4.2, and yeah, and we talk about more changeable basis in 4.3. Yeah. And yeah, so we see that in 4.2 we have a lot of in this 4.2.3 we see that we can choose different bases in Rn and different bases in Rn. Okay. So we have this E and F that we can choose pretty arbitrarily. And we look at this situation a little more detail in terms of linear operator in 4.3. We find out that sometimes we can we can represent the same operation, so same L with a different A by changing on basis. Okay. And so if we are in this 4.2.3, then this is fully general. This is a bit too general. We can choose whatever E here and whatever F here. Okay? And in 4.3, we do this in a bit more restricted. So we are studying linear operator. And remember, linear operator is something that map from a space to itself. Okay? So we have some n-dimensional space V, and it maps to V. And we map back to V by this L. Okay? And so L we can have some matrix representation of L, and this matrix representation now will depend on just one basis because I guess you can choose 2 bases, but with 1 basis more nature because you are just back to this you are back to this space V. So we want this space V, we want to have order basis chosen, and different order basis chosen will have a different matrix representation. Okay, and yeah, so we'll see that you can express a relationship between different matrix representation of the same operation. Okay, and so idea is kind of this. So we have our familiar square here. But we are doing linear operation. So once again, we have L here, and we have A sub L, and here we don't really have W, so W is V here, and then if you think about V is n-dimensional, then obviously this V here is also n-dimensional. So maybe let's write a bit of cross out to have this comparison here. So W is now V, and Rn is still Rn. Okay, and yeah, so now we don't have a different E and F, so this thing is still E. Okay, and now have another square. Okay, so we have this E or C. Okay, so we will have this mapping that will say you have E here and E here, and that will dictate the mapping between this V and X and this W and Y here. And I guess here we should go back to Y, and X equal to Y equal to Y equal to W sub E here. Okay, and so we have a basis E, but we can do another change of basis to some basis F. So we can have a basis F that some basis F that change from E to F, and basis F that will have coordinate with the starting point and the coordinate of the end point. Okay, and so in basis E we have some matrix A. So now this is I guess A sub. I guess let's write this as a function. A is a function. Let's just write A. So A corresponds to E, and then we can have so this is A sub L. So everything is correspond to L, and we can have another B of L that corresponds to this basis F. So if we change the basis here and the basis here, we can have another matrix B here. And what this basis B will be is so a bit of a spoiler. The basis B will be you need to change it to A and do transformation here and change basis back to F. So you need to change basis from F to E, and we already know how to do that. The matrix to do that is called a transition matrix. It's called S. Okay, so we need to do the transition matrix from coordinate in F to coordinate in E, and we need to do A, and then we need to change our coordinate back or change our basis back with this S minus 1. So the total matrix B is S minus 1 AS. And this is basically all we want to talk about in this section. But that's a lot of spoiler. But let's see this in much slower build up. Okay, so let's see these examples. So we start with R2 example. So let's have some linear operation from R2 to R2. Okay, so L of x equal to 2x1 and x1 plus x2. And we know how to find the matrix representation of this. So we map L of E1 and L of E2, and L of E1 will be this thing will be 2 and 1 here, and L of E1 will be just 1 here. So 2, 1 and 0, 1, and we just put them into a matrix of 2, 1 and 0, 1. This is our matrix of L. Okay, with respect to E1, E2. Okay, and now let's do a change of basis, and we can think about this kind of geometrically. So you think about E1, E2 is the coordinate with respect to the standard X and Y coordinate here, and then maybe we can have a basis in different direction. Maybe we want a basis in this 2D direction, and we want to see how the coordinate in this basis change. And so that basis will be like U1 and U2, although they are not unit vectors, so it's a bit weird. But anyway, the idea is roughly like this. We want to rotate our thing by 45 degrees and see how the coordinate change. Okay, and so we have U1 and U2. U1 equal to this 1, 1 vector, U2 equal to -1, 1 vector. Okay, and then because we are from Rn to Rn, so actually we don't need to look at the 4.3 section, so we already know how to do this. We can do this theorem 4.2.3, and we have a basis here and a basis here, and they are just the same basis. Okay, and so how we find the matrix is we want to find L of U1 and L of U2. Okay, L of U1 equal to 2, 2, and L of U2 equal to this -2, 0. This is just we can either do a bit of a bit of build up from this A here, or we can directly look at this. Either way, it's very similar. We can calculate L of U1, L of U2, and yeah, and then basically we need to do our Gaussian elimination thing, but here we do this slower because we want to see a formula. So if we want to do this slower, then we want to see how to transform from this basis back to standard basis. Okay, so from U1, U2 basis back to standard basis, then basically what we need to do is multiply by U minus 1 as our. Okay, so let's jump back again. So yeah, as we see here, we want to multiply on it by this B minus 1. And the B, we just call it U here, so this is when we want to multiply by U minus 1 here. Okay, so this U minus 1, well, you can write down your U1, U2, and you can calculate your U minus 1. Okay, so skip the calculation, you calculate U minus 1. And yeah, so our basis vector will be U minus 1 on L of U1, then U minus 2, our column vectors for our matrix representation now is U minus 1 on L of U1, and U minus 1 on L of U2, and it's yeah, it's this matrix. It's 2, 0 and minus 1, 1. Okay. And yeah, and we can see kind of a generalization of this example. So what we do here is we have a U minus 1 on L of U1, and L of U1 we also know that in standard basis notation is just A times U1. And then the second column is U minus 1 on L of U2, which is U minus 1 on excuse me, just A times U2. Okay. So this is kind of why we want to see this as A times U1 and A times U2. And we see the first column is U minus 1 on A on U1, and the second column is U minus 1 on A on U2. And you can think about this block matrix multiplication, and you see that this is just U minus 1 times A times this U1, U2, both two columns matrix. And U1, U2 once again is just this U matrix. So the total matrix B is U minus 1 on A, and U minus 1 times A times U. Okay. Yeah. So linear operator can have different matrix representation in different bases. Okay. So we now change it from standard basis to basis U, and we see that you need to kind of sandwich your A with U and U minus 1. So you have U minus 1 and A and U. Okay. And yeah, so this is our conclusion. So you go to standard to yeah, so you want to go from standard to U, then you need to do this U minus 1 AU. Okay. And then we have our theorem. So you want to be for general. For each general, then we have two different bases for our. So we now still have two different bases, but it's different from chapter 4.2. 4.2, those are different bases for different space, but now we just have one space V. So we have a different basis for the same space V. Okay. And we want to think about linear transformation from V to V, so basically a linear operation. Yeah. And yeah, so we can use the transition matrix S to change from matrix representation with respect to E to a matrix representation with respect to F. Okay. And B will be this S, A, S minus 1. And S is a matrix that will change coordinate of F to coordinate of E. Okay. And yeah, we write down the proof here, but I guess the proof basically, let's look at this once again. Proof will just be that the idea is you want this B, and you already know how this A works. So you use S to change coordinate to this thing from F to E, and then you map here. Okay. And yeah, and then you multiply by A to get mapping here. Then you get S minus 1 to change back to the coordinate here. Okay. And yeah, so we have a whole bunch of x, y, t, z here. So we start with some coordinate x here. Then we have y being the coordinate here, s, y. And t equal to a times y. So we just multiply by a. So map the coordinate here to coordinate here. And yeah, then you map to here. And and this z should be s minus 1 on t. So this is s minus 1a on y and s minus 1a sx. Okay. And yeah, then we can try to read through this more algebraic proof here. And I guess I guess it's a more detailed proof here. So we have whatever x that is a coordinate I guess here we have a typo. So we should have any vector v inside Rn, and v being inside any vector in Rn, and x being the coordinate of v with respect to f. Okay, so yeah, so v has this s coordinate, and yeah, we have s as a transition matrix from f to e, and then yeah, y will be the coordinate of v with respect to e, and from yeah, it's basically just this thing, and we will know that y will equal to s of x. Okay. And yeah, I guess here the writing is weird, so we want to say yeah, so basically we write down the thing. So because S is a transition matrix, then we know that from S being a transition matrix, we know that this y vector will be the coordinate with respect to E. Okay, so from y equal to xx, then we get this thing. Okay, and yeah, so V is this thing. Okay, and yeah, and since A is the representation of L with respect to E, and so we know AY will equal to this thing, so T will be equal to L of V with respect to E, and yeah, and then finally we use Z as a transition. So I guess Z we should define as oh yeah, and Z is the representation of Z is B times X. This is a representation of sorry. I guess this I don't like this definition here. Okay, and Z, I think here we should define Z as equal to yeah, it's a weird order, but we don't have a B defined here, so we cannot really define Z as Bx. So I guess we should just say Z equal to S minus 1 S minus 1 T. Okay, this will be easier. S minus 1 T. And yeah, and if Z equal to S minus 1 T, then yeah, then T is L of V with respect to E, and then Z will be L of V with respect to F. Yeah. Yeah. And yeah, and then we multiply everything out, then we will see that Z will equal to, okay, so let's change the ordering of all these things. Okay, so this is the definition of Z, so we should have from this here to here, and then we just string together things. Okay, so let's write things in other way. So z will equal to s minus 1, and a and s x, and then we just define this thing as b, and yeah, we see that z equal to b times x. Okay. Okay, and yeah, so this is our theorem, but the idea is you go from this block, so you go here, here, and here, and you see this is s minus 1. And I guess a bit of keeping track. So remember, when you do multiplication, you go from right to left. Okay, so you're starting with s here and a and s minus 1. So just don't get the ordering wrong. Okay, or like because when you write down equations, you write from left to right, but when you resolve this multiplication, you actually resolve from right to left. So this is a little bit different, and don't get messed up. Okay, and yeah, so that's the result. Okay, so we have that we have well, we want to do change of coordinate for our linear operation, then we need to do this s minus 1 as. Okay, and then now we want to talk a bit of structural idea about this s minus 1 as. Okay, so if you want to calculate this, then it's just a special case of our 4.2.3, right? So once again, remember we already have our 4.2.3 tells us basically how to change the coordinate in more general way. You can change the coordinate here and then change the coordinate here. Okay. But so why do we want to restrict to linear operator? Is because we want to find a different way to express the same linear operator inside this space. Okay. So we want to think about what the representation of a linear operator can be inside by choosing different space of yours and by choosing different bases for yours and space. Okay. And yeah, so we first give a definition of we say two matrices are similar if you can write. I guess the definition here is one side. So we say B is similar to A if you can change from A to B. So you can find some S, which is a transition matrix, but here for now it's just a non-singular matrix. You can find some S such that B equal to S minus 1 AS. Then A and B are singular. And then they are similar. Sorry. And yeah, so A and B are similar. So B is similar to A if you can find this. And you keep saying A and B are similar because this property is transitive. So if B is similar to A, then A is also similar to B, because we can just write A as so now we just change S and S minus 1. A is S minus 1 to the minus 1 times B times S minus 1. Okay, so this is easy verify. If B is M minus 1, A and S, then SB S minus 1 equal to A. Okay, so A is S minus 1 to the minus 1, and times B times S minus 1. So if B is similar to A, and then A is also similar to B, and we say A and B are similar matrices. So yeah, we can link those matrices together, link different matrices together by this similarity relation. Okay, so every square matrix we can think about what are similar matrices to it. Okay, if you think those square matrices are linear operations, then there are many different matrices that are similar to it. Okay, and yeah. Here is an example. So let's say we have a linear operation that's defined by this matrix A. Let's say it's a quite complicated form: 2, 1, 1, 2, 1, 1, and 2, 2, 0, 2, 2 here. Okay. And yeah, so A is yeah, so A represents this L with respect to center basis. And then we try to find some B that's similar to A, and let's say our B has the basis element y1, y2, y3 equal to this 1 minus 1, 0, minus 2, 1, 1, and 1, 1, minus 1. Okay. And yeah, so we can do calculation here, and in general we should calculate this s minus 1 as, but this is a nicely set up example, so we can do this calculation actually a bit faster. So we see that when we have y1, y2, y3 on A, and they actually go back to also y1, y2, some linear combination between y1, y2, y3. Okay. So we have a y1, we actually equal to the 0 vector, and yeah, it's 0 times all the y's, and a y2 equal to actually just y2. So if you do a matrix multiplication, it's just y2. Okay. And yeah, and ay3 is actually just equal to y3. Okay. So so a bit of spoiler, but you probably already know this in high school. And so y1 and y2 and y3 are called the eigenvectors of this matrix. Okay. So those are the vectors where you multiply by this matrix and you go back to those same vectors. Okay. And so you see that if you have those eigenvectors as the basis for your matrix, then with respect to this matrix, okay, and now you don't need to do the minus 1 of the basis because you already find a coordinate. So coordinate is 0, 0, 0, 0, 1, 0, and 0, 0, 4. And yeah, then you see that we have a very nice form as the representation of our linear operator L. So L is now just this diagonal matrix with 0, 1, 4 as diagonals. Okay. And yeah, a bit of a spoiler, chapter 6 is called the eigenvalues. Okay. And yeah, we can verify that D actually equal to s minus 1 as with our formula. And yeah, so s is just y1, y2, y3, so it's this 1 minus 1, 0, 2 minus 2, 1, 1, and 1, 1, 1. So just list y1, y2, y3 here. And then we skip the calculation of s minus 1, but s minus 1 will equal to this matrix, and yeah, you can verify with the matrix multiplication. Let's see that in terms of this y basis, our linear operator actually has this nice form. And yeah, so this kind of thing is called diagonalized, and we'll study that more in chapter 6. Okay. But yeah, for now we have this chapter. We have our 4.3 is a bit of a special case of our theorem 4.2. Special case of our theorem. Let's write it here. 4.2.3. It has two bases, but now we have the same space and the same basis. And we see that we can change between those same bases and get a different representation of our linear operation. And yeah, sometimes the linear operation will have, or matrix will have a very nice form. And this will tell us a lot about our matrix. Okay. And yeah, but for now we want to know how to do this transformation, and we want to remember this idea of similar. So similar matrix means that you can go from one matrix to another matrix by doing this sandwiching between s minus 1 and s. Okay. And yeah, so that's a lot of changeable bases. We will see more changeable bases in chapter 6. And I guess let's say a little about spoiler. So diagonalization is a very nice tool because you see that well, first of all, in diagonal form the matrix just looks very simple. So instead of 9 elements here, you basically only need to trigger over 3 elements here. And yeah, so a lot of time you want to diagonalize your matrix, and it lets you do matrix multiplication basically easily, because you see that you apply your matrix on eigenvectors, then you only get the constant vector, etc. Okay. And yeah, but that's much later part of the course in chapter 6. And on Wednesday we'll start on chapter 5, which is about orthogonality, and yeah, we'll talk about more geometry of our linear space. We are now actually getting angles in our linear spaces. Okay, yeah, that's in chapter 5. Okay, so see you on Wednesday. We'll start on chapter 5. Okay.